Welcome to this video in the nuclear chemistry chapter. Today we're going to be covering half-life and half-life calculations. So if you haven't already done so, please make sure you have downloaded and printed your companion worksheet. You have your New York State chemistry reference tables handy and a periodic table out. And of course, you have your calculator and a writing utensil at your disposal. So without any further ado, let's get started. So the first thing we have to talk about is exactly what half-life is. And half-life is essentially the time it's going to take for one half of the atoms, we're talking 50%, of a radioactive isotope to undergo radioactive decay into a stable isotope. And what that really means is these particles are actually going to be spitting out their nuclei, as we had seen in previous lessons, to reach a stable ratio of neutrons and protons. And this happens in a predictable manner for the many different radioactive elements that are out there. One of the things that's important to note is that half-life is not something that you can increase the rate of like we saw in chemical reactions earlier in the year. Half-life is not dependent on temperature or pressure, so there's no way to speed it up and no way to slow it down. It happens at a constant rate. So to make the introduction to this concept a little bit easier on you, I'm going to throw it to a video that I found online that makes half-life a little bit more palatable and presents it in a unique way. Make sure you take notes on what the video has to say, and I will be back after this short clip.
This is Klaus, and he asks himself, what does the term half-life actually mean? So let's imagine Klaus has a flock of sheep. All of the sheep are very jittery, but after one day, half the flock has calmed down. But be careful, that doesn't mean that by the next day, the whole flock has calmed down. Because after the half-life period of another day, again only half of the remaining jittery naughty flock will behave as they should. This continues and so on and so forth, until at some point the entire flock has calmed down. Therefore, in this case, the half-life of the naughty black sheep of the flock would be 1 day. If half of the sheep became well behaved not in 1 day, but in 1 hour, the half-life of the sheep would be exactly an hour. Thus the flock would also calm down much more quickly. The same also applies to radioactive materials. Radionuclides have a half-life too, during which half of the materials decay. In this process, other radionuclides form, which in turn decay as well. Here too, the period in which exactly half of the material decays is also called half-life. There are materials with very short half-lives, so these decay very quickly, for example, in a few milliseconds. Other radioactive materials have half-lives of several million years or even much longer. Anyway, Klaus's sheep have all calmed down, and now he's looking forward to enjoying some delicious sheep's cheese.
So obviously for us, we're not really talking about Klaus and his sheep. We're really talking about radioactive elements that are undergoing decay and the time it takes for them to undergo such a process. And I hope it was clear from the video that when one half of the particles undergo decay and turn into something new, that is a half-life. And here we can see our example, and we're dealing with newly formed rocks. 100% of the atoms in there are radioactive, but after one half-life, which in this case is 1.3 billion years, 50% of the particles have turned into something else, and 50% are what the original radioisotope was. And this goes on and goes on. In another 1.3 billion years, we will wind up now with only 25% of our isotopes being what the original was, and then 75% being something else. And after another half-life, we take another half of the original and cut it in half, so you wind up with 12.5%. And then finally, after 4 half-lives, 6.25%. And what that time takes is essentially 1.3 plus 1.3 plus 1.3 billion years for a total of 4 half-lives. To illustrate a little more what I mean by this, we're going to throw it to jolly old England, where you're going to watch carbon-14 decay.
Let's look at carbon-14, and we'll represent the unstable nuclei as red and the stable nuclei as yellow. So carbon-14 has a half-life of about 5,700 years. So at time equals 0, all the atoms are unstable. But as time progresses, nuclei start to decay at random until, at one half-life, 5,700 years, half of the nuclei have decayed and are now stable. As time carries on, nuclei carry on decaying, but it's happening less often until after 2 half-lives, the number of unstable nuclei have halved again, leaving only 25% of the original unstable nuclei remaining. As we progress along, we can see that the number of decays happening is decreasing even further, or the activity of the source is decreasing as time goes on. Actually, we can also say that half-life is the time taken for the activity of a source to decrease by half. So finally, as time is progressing, we get to 6 half-lives and only 1% of the unstable atoms remain. And this has taken us 34,200 years. Now let's quickly look at another nuclei, iodine 123. Now this has a half-life of only 13 hours, so it will still take 6 half-lives to reach 1% unstable nuclei, but it will do this much quicker, in only 78 hours. So, what are the key points to remember? Well, we need to remember that nuclei decay spontaneously and at random, and it's impossible to know when this will happen for individual nuclei. So instead, we use the concept of half-life, which is the time it takes for half of the unstable nuclei to decay.
All right, fun video from the UK. And one of the points that he did make in the video is that even though initially it seems like everything is decaying much faster, it's really an optical illusion simply because there are just more atoms that have not undergone decay. After 1 half-life, now there's 50% less atoms that could possibly undergo decay, so it seems like decay is slowing, but the reality is it's happening at the same rate. There are just fewer atoms that are turning into, let's say, lead-207 or whatever a stable isotope winds up being. So now back to the chemistry stuff. If you guys want to engage yourselves in some half-life problems, one of the things that you are going to need is CsRT Table N. CsRT Table N is your selected radioisotopes table, and what's cool is they list them alphabetically. That's here, and I know you saw this before when we were doing decay modes, but now we're going to deal with the second column here. That is half-life. It tells you what the half-life duration is for each of these radionuclides that are here. And you'll notice that some are days, some are years, some are milliseconds, some are minutes. And what your big takeaway from this has to essentially be is that the longer a half-life is, the more stable a radioisotope will be. So, for instance, carbon-14, which they used in the example that we just saw, was 5,700 years approximately for a half-life versus calcium-37, which is 182 milliseconds. So this is much more unstable and decays far faster. In order to do all the mathematics and the problems that we're going to throw at you properly, you have to have in your pocket the most important formula that there is, and that is N equals little t over big T. This is a formula that is used to calculate the number of half-lives that have passed in a specific problem. So what we see here is N is number of half-lives passed, N is for number, little t is for your time that has elapsed, and big T is the half-life of your radioisotope, either from table N or if the question happens to give one to you. Okay, let's jump into some sample problems. We'll show you how to use the formula, how table N corresponds to the questions, and of course you're going to need your calculator. So let's grab all that, get that handy, and get going. So the key to attacking these questions is really to see what the question is giving you so you can know how to go about solving it. So in our first question, we have 16 grams of cobalt-60, and we know that time elapsed has been 15.813 years. They want to know what mass in grams of this sample is going to remain. So I'm going to teach you how to do this one using the chart. There are multiple methods that you can use, but the chart is going to be a good one because it can give you everything, and it is non-destructive in terms of math. There is easy math with this, so I know everybody can handle it. So the way we're going to go about doing this is we have to see, well, how many half-lives have passed in that 15.813 years. Otherwise, we're not going to know how much of our sample we have left. And the way we go find out how many half-lives have passed is we look at table N. So here is cobalt-60, and we can see its radioisotope half-life is 5.271 years. So if I know that number of half-lives passed equal time elapsed over half-life, I can now substitute in using this equation. So here's my equation, N equals 15.813 0.813 years divided by 5.271 years, and that is going to tell me that 3 half-lives have passed. So now I can start to think about, well, if 3 half-lives pass, and I start with 16 grams, I'm going to just fill the chart out. 1, 2, 3. Every time a half-life passes, you guys know you have half of the original sample. So after 1 half-life, you have 8 grams. After 2 half-lives, you have 4 grams. And after 3 half-lives, you have 2 grams. So we would have 2 grams remaining of cobalt-60. And that's how you would do those questions. Let me show you a second method to do this. This is what we call the horizontal method, and you guys will understand what that means in a second. You still have to use this formula to figure out how many half-lives have passed, but once you do that, we can start with the original mass, which is here, and then since we know 3 half-lives passed, we can just put in 3 half-lives, and then just extrapolate out this way to get 2 grams at the very end. So it's very simple to do these problems, whether you're going to use the chart or whether you're not. So I don't care. It's really up to you. Do what is best. And of course, there is a way to solve this mathematically, which we can get to in the end of the video. All right, here is the next question. This is example 2. It says most chromium atoms are stable, but chromium-51 is unstable with a half-life of 28 days. What fraction of a sample remains after 168 days? Got to approach this the same way. We got to know how many half-lives have passed if we're going to know what the fraction of the sample is. And when they ask for fraction, they are talking 1 over 1, 1 over 2, 1/2, 1/4, 1/8, 1/16, etc. We're going to approach this in the alternative fashion and show you guys how to do this without the chart, since I really focused on the chart in the last question. Let's see how many half-lives pass. So I know that the time elapsed has been 168 days. And I know that we started with a half-life of 28 days. So the number of half-lives that have passed will be 6. So now we are going to start with our fractions. Everything starts as a whole, so that's 1 over 1. And now we're going to go 6 half-lives. And after 6 half-lives progress, we wind up with 1/64th of the original sample that we had. Make sure to take note that every time you add a half-life in, you are dividing your fraction in half. So 1 over 1, 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 1 over 64th, until you get to the number of half-lives you're trying to get to. I thought it'd be worth it to show you the second example using the chart as well. So once we solve for n, our number of half-lives that pass, we are going to now write them in here. We know we are going 1, 2, 3, 4, 5, and 6 half-lives. And since we are looking for a fraction, we are starting with 1 over 1. That gives us a half, a quarter, an eighth. You notice every time I'm doing this here, I am just multiplying by 2 to make my fraction smaller. And eventually we get what we are looking for. After 6 half-lives that pass, we have 1/64th of our sample left. Once again, it doesn't matter whether you use the chart or you use the horizontal method. Either way is going to get you there, but it all starts with the magic formula for half-life, n equals little t over big T. Let's move on to the next example. All right, now it is your turn. Here's example 3. Why don't you guys try and figure out the answer to this question? What's the half-life of a radioisotope of 25 grams of a 200-gram sample remains after 11.46 days? Lots of information, so remember, take what you know, start there, and then work your way through the problem. So pause the video now, and then check the answer when you are done. Okay, if you did this correctly, we should get that 3.82 days is the half-life of this sample. Now, how did we get that? Well, so what we had to do is see how many half-lives it would take to get from 200 grams down to 25. So I did a little bit of math. And you notice I did it here. I started with 200, cut it in half, 100, cut it in half, cut it in half, and then I filled in how many half-lives it would take. It actually might be a little clearer looking at the horizontal method. So you can see I started with 200, underwent 1 half-life to 100, another half-life to 50, another half-life to 25. That got me what I was looking for in the question, and that tells me it took 3 half-lives. So if I knew that the number of half-lives elapsed was 3, and I knew that 11.46 days passed, I could then mathematically calculate the half-life. So I really just wound up solving for x here. 3x equals 11.6, and I got 3.82 days. Not too bad at all. All right, here is example 4. This is for you to try. Pause the video now. See if you can figure out the answer and the mass of the original sample. Use whatever method you want. Okay, if you did this correctly, we should have gotten 16.0 grams in the original sample. This question was unique because I actually had to work backwards here, understanding that 4 half-lives have passed, because they told me that 1 gram was left after 116.5 years. So you'll see here is the order I did it. I looked for the half-life on table N for strontium-90, and it says that my half-life was 29.1 years. And then I plugged that into my formula, which was here. N equals little t over big T. I said, all right, how many half-lives have passed for me to be able to do that? So knowing that 116.5 years have gone by, I used the half-life from table N, which is 29.1. That tells me that approximately 4 half-lives had passed. I filled in my table here all the way down to 4, and then I worked backwards. I knew after the 4th half-life that I had 1 gram of my sample left, so then I worked going this way, saying, all right, so twice 1 is 2, twice 2 is 4, twice 4 is 8, etc., etc., and that got me to my original mass of my sample, which was 16. So either way I did it, I needed to utilize the same information. I needed to utilize what was on table N, and of course, I needed to utilize this equation, which was here. Question 5, pause the video, give it a shot, and then unpause when you're ready for the answer. Okay, if you guys did this correctly, you'll see this was a 3-step method from me. I needed to start with 64 and then work my way down to get the target mass, which in this case was the 2 grams that were remaining. So I kept taking a half of 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 a half until I got those 2 grams. And then I saw how many half-lives that was. At that point, I plugged it into our equation, which is N equals little t over big T, and I was solving for the half-life of the material. I knew how many half-lives passed. I knew how many hours had elapsed, and that got me a half-life of 2.5 hours. All right, question 6. This one is for you to do. Pause the video now and then unpause when you're ready for the answer. Okay, if you guys did this one correctly, we should have gotten 464 grams. Once again, I'm taking all the information in the question. Half-life of 5.26 years. Storage time, 26.5 years. I'm figuring out that 5 half-lives passed. I'm listing them down in my chart. And then it's telling me that in the end, I got 14.5 grams of cobalt-60. So now I am working my way back up and multiplying by 2 each time. And I wind up seeing that when this first went into storage, there was 464 grams of cobalt-60. But after those 5 half-lives, it wound up back down to 14.5. So for all the mathletes in the house, here are going to be some mathematical formulas which you can apply when you have half-life questions that give you half-lives that do not come out to a whole number, such as we have seen this entire time. Let's check these out. You'll notice the first formula you already recognize. This is used to calculate the number of half-lives passed. But now here is an alternative formula. When you want to calculate your percentage or your fraction that's remaining, you will take 0.5 to the nth power. The nth is the number of half-lives that pass, so you can actually enter this in your calculator as a decimal if you really needed to. If it was like, let's say, 2.8 half-lives that passed instead of 3. And our third formula is a great one. Make sure you take it down. It's used to calculate how much of your original sample remains when you've undergone a certain number of half-lives that may or may not be whole numbers. So you would just plug in the information you're given and solve for the 1x that you are not given. So I know the video is getting long, but I wanted to give you a chance to try the mathematical formulas. Remember, these are optional. Make sure you have the first 2 ways of solving half-life in your pocket and ready to go. But these will definitely help you through when we have more complex half-life questions. So as we put the question up, pause the video, try and apply these formulas, and then unpause when you're ready for the answer. Okay, here's question 1. Pause the video now and apply one of the 3 formulas you were just given. Unpause when you're ready for the answer. All right, if you did this one correctly, we should have used the big formula. Amount remaining equals original amount times 0.5 to the number of half-lives passed. And you'll notice here is my methodology for solving. and we wind up getting 2,500 atoms. Here is question 2. What percentage of iodine-131 remains after 27 days? And you're going to have to go to Table N and dig out the half-life of iodine-131. So pause the video now and let's see if we can solve what percentage remains using math. Okay, if we did this correctly, you guys should get 9.7% remaining. How did we get that? Well, we took our half-life equation and we figured out that 3.366 half-lives had passed after pulling our information out of Table N. And then, since it wants percentage, I applied it here, that it's 0.5 to the n power. You'll notice that I raised the 0.5 to that decimal, which is why we have to use the math formula. I did get a decimal as my answer, and to turn it into a percentage, I did have to multiply by 100. So never mind the sig figs, but that is pretty much how we would do this one. All right, our last example is dealing with gold 198. Pause the video now and then unpause when you are ready for the answer. Right, if you did that one correctly, we were using the big formula that was here. We started the same way, had to dig out the half-life of the gold 198 from Table N. Once I did that, I found out that I got a fractional number of half-lives that passed. It's not a whole number, it's 2.597. And so I plug that into my formula, and we see we get 13.2 grams of gold 198 remaining. So these are certainly more complex because you're dealing with decimals and fractional half-lives and all this different stuff. But I would say that it is a much quicker way to solve it. And if you memorize these formulas, you can actually do any half-life problem. But for which you'll be responsible at the end of the year in June, all you have to know how to do is the 2 methods that we did in the beginning of this video. So apologies that it was so long. If you want a little more practice, try these 3 questions now. Pause the video and then unpause for the answers. All right, if you did it correctly, here is what you should have gotten. Remember, if you have any questions about half-life or anything that we did in this video, make sure you bring them up in the burning questions segment tomorrow. And that is it for me. This has been a long one, but certainly a lot of explanations that are there. I want to make sure that you understood half-life. It has been a distinct pleasure to be your teacher and take you on this journey through half-life. I will see you all on the flip side. As always, peace out.
That's all, folks.